6.1 Area between curves. Take a minute to read the two essential questions. In essence, what we're going to be doing is finding the area between two curves by finding the area between the upper curve f of x and the x-axis, finding the area between the lower curve g of x and the x-axis, and subtracting those to get the desired result. Now you can see that the area between the two curves will be broken down into rectangles. This is going to represent a Riemann sum. Let's go to the exploration. The Riemann sums are midpoint rectangles, but we certainly could do left-hand or right-hand point Riemann sums. We'll stick with the midpoint. And the idea is to increase the number of rectangles because that increases the accuracy. So the area of a region between A and B will be the difference between the two functions, and that's what is illustrated right here. Okay, let's go ahead and put it in practice. What we like to do is I like to set up a little representation for area, and I like to call it delta A, and it's going to be the y of the upper minus the y of the lower. That's going to give the height of the rectangle times delta x. So here's my rectangle, y of the upper minus y of the lower. That's going to give the height times the width. Now the upper is e to the x, the lower is x, delta x. Now what I'd like to do is add up all these rectangles, and so that means I'm going to have a summation. So I equal 1 to n, and I'm going to have my I representation for each rectangle. And to have the best accuracy, of course, is to take the limit as n approaches infinity. And that will give me my exact area. We can go ahead and translate this into an integral, and the delta x's are going from 0, 0, so our x equal to 0 to x equal to 1. And then I write the representation of the rectangle, e to the x minus x. That represents the height, and then dx. Now why is it no longer delta x? Is because once you take this limit, we have that dx representation. Let's try another. Again, delta A, always set up your representation for your small piece. And that's going to be the y of the upper minus y of the lower times, and the width will be delta x. The y of the upper is actually the parabola that's facing down. So that's going to be 2x minus x squared. And the lower will be the parabola that's facing up, which is x squared. And I'm going to again sum up I equal to 1 to n, 2 x sub I, and I'm going to combine these minus x sub I squared delta x sub I. And the true area will be equal to the limit as n approaches infinity of this summation. So we can write the area as an integral, and the x's are going from 0 to 1. And I'll write my representation. And I made an error here. This should have been a 2 here because there's 2 of them. And I'm going to have a 2 here. And then this changes to dx. And then just put it in the calculator to find our area. Now your turn. Stop the screencast and attempt to do these problems. And here are the answers. Drawing the rectangle is a very good idea. Setting up your small piece of area and then setting up your integral. So this is what we want to do. We want to, if not given to us, we want to find the points of intersection. So I took my calculator and I found that this point was 1.181, go to 3 decimal places, and the other point was 0, 0. And set up your delta A. So delta A is equal to y of the upper, which is going to be x over root x squared plus 1 minus y of the lower. Make sure to put that in parentheses. And then my widths of my rectangles are going to be delta x. And you don't have to go through the summation process. You can actually go right to the integral if you wish. And we're going to go from 0 to 1.181. And we can go ahead and write the representation. If you want to distribute at this point, just make sure you have accuracy. And again, this changes to dx once you've taken the limit. All right, what happens if the curve intersects at different points? What will happen is your upper and lower will exchange, and when that happens, this area, if you've represented them all with f of x minus g of x, some of these areas will now be negative. To avoid that, what we can do is we can take the absolute value so that when we go through these three areas, they'll all be positive. So let's take a look at an example right here. We have two areas. If we take the area and go from 0 to pi halves, we're going to get 0 area, which we know is not happening. So what we could do, one, is we could figure out area 1, making sure that you understand that this is the upper, y of the upper, minus y of the lower, and that's going to yield a positive answer. Now right here, it reverses, and so the y of the upper now is different, minus y of the lower, and this will yield a positive result because I exchanged the upper and the lower. The other thing you could do is just find the area 1 and double it because this looks very symmetric. The other thing you can do is what was suggested on the previous slide, is you go from 0 to pi halves but take the absolute value of it so that no negative areas will be canceled. What happens when you have two curves? These will be curves and not necessarily functions that you want to find the area between in terms of y. And what we're going to do, instead of having upper and lower, we're going to have x of the right and x of the left. X of the right and x of the left. You want to take the x of the right minus the x of the left because that'll yield a positive number. And then your widths will now be delta y's instead of delta x's. We write the relations in terms of y. We go ahead and do the summations as we did before, and then we can write the integral. Now let's take a look at this problem. Sometimes we don't recognize that the rectangle should be sideways instead of upper and lower. So let's go ahead and try to do an upper to lower. You can see it looks okay. Where it's not okay is right over here. So in this region right here, we have the same curve that we're finding the area between instead of two distinct functions. So let's approach it in a different manner. Let's go ahead and draw the rectangle sideways. So our delta A will be x of the right minus x of the left, and the width will be delta y. So x of the right, that's going to be our line right here, and we're going to solve for x, and it's already been done for us. So this is going to be y plus 1 minus, and then what we're going to do here is we're going to solve for x, which they've done for us over here, and then we need to put this in parentheses, 1/2 y squared minus 3, and then delta y. Now, why are we doing this? The reason we're doing this is because everything has to be in terms of the integral, the variable of integration, which is y. So once we figure out it's delta y, the integrand must be in terms of y as well. Okay, so our area will be the summation of I equal to 1 to n, and this is going to be y sub I plus 1 minus 1/2 y sub I quantity squared plus 3, and then delta y sub I. And again, To get better and better accuracy, you get more and more rectangles, and that'll yield the area. And this is going to be over y's that are from -2 to 4. And we can write our integral from -2 to 4, and we'll have y. I'm going to add the numbers together, minus or plus 4 minus 1/2 y squared dy. Okay, your turn. Go ahead and draw your rectangles, appropriate rectangles. You can avoid the summation of the rectangles if you wish and go right into the integral. And here's the answer.